Next problem. A charge q is uniformly distributed over the surface of non-conducting disk of radius r. The disk rotates about an axis perpendicular to its plane and passing through its center with an angular velocity omega. As a result of this rotation, a magnetic field of induction B is obtained at the center of the disk. If we keep both the amount of charge placed on the disk and its angular velocity to be constant and vary the radius of the disk, then the variation of the magnetic induction at the center of the disk will be represented by the figure. So the situation is something like this. You have a disk. This entire disk has been distributed uniformly with a charge q, and about an axis which is passing through the center and normal to the plane of the disk, it is rotated. Now, as a rotation of the charge, there is a magnetic field at the center B. We have to find out the relationship between B and R, where R is the radius of the disk. Okay, now let us say this is the disk, and in this entire disk we assume a small elemental ring of radius r and thickness dr. Okay, so the total length of this elemental ring will be 2 pi r dr. Okay, now since the charge is distributed uniformly across its entire area, so surface charge density sigma will be given by total charge q upon pi r square. So the ring having a area dA, that is equal to 2 pi r perimeter into dr thickness, will be given by dq equal to sigma dA. Okay, now this value is equal to q upon pi r square 2 pi r dr. Okay, so pi will cancel out and we will have 2q upon r square r dr. Okay, now this is the total amount of charge which is rotating with, let us say, frequency f. Then the small elemental current that this elemental ring constitutes, di, is given by charge dq into its frequency f, which can be written as dq times omega by 2 pi. Okay, now if we substitute the values of dq here, we will get 2q upon r square r dr times omega by 2 pi. Okay, now this value of current di is now equal to 2q by, sorry, 2 will cancel out, so q upon pi r square omega r dr. Okay, now because of this elemental current di, there will be a small contribution towards the total magnetic field, and that contribution is dB, which is given by mu naught di by 2r. Okay, now if we substitute the value of di here, the value of dB will be now equal to mu naught upon 2r, and di is q upon pi r square omega r dr. Here rr will cancel out and we will have dB as equal to mu naught upon 2 pi r square q omega dr. Okay, so if we integrate this expression, okay, we will get the total magnetic field with the limits r equal to 0 to r equal to capital R. So we will get B as equal to mu naught q omega 2 pi r square, and integral of dr is r. When you substitute the limits, we will get r, and this r will cancel out with this. So B is equal to mu naught q omega upon 2 pi r, which implies that magnetic field is inversely proportional to r. So we will get a rectangular hyperbola curve, this kind of curve. Okay. So among the 4 options given, option A is the correct one.